between curves, and we know that's integrating the top minus the bottom if we were dealing in terms of x. And if we were dealing with y's, we had to do right minus left. So the next piece is talking about volumes of solids. And my art is very lacking, so bear with me on this. So I included some figures from the book to kind of help you visualize, because I know I can't draw at all. So if we think about like a cylinder, okay, if you think about a can, you have the base, same on top and bottom, and then you have the area in between, right? So this one is an oddly shaped cylinder, but volume is basically the area of the base times the height, whatever that would turn out to be. And we can do that with regular cylinders. When we talk about those, the formula is pi r squared h, because the base is a circle. The area of a circle is pi r squared, and then take that times your h to get the volume. Volume of a box. Okay, the base is a rectangle, so that's your length times width, and then to get the volume, you take it times the height. So when we're talking about volume, it's area of the base times the height. If we need to calculate volumes, so if we have some kind of solid like this, if we had an irregular solid, we don't just have a set formula for it. But we could think of a cross section, which is like if you take a slice out of the middle, what are you looking at? So an irregular shape, maybe if I'm talking about a pear. Okay, if I slice my pear horizontally, what shape are you looking at? A circle. Now, is the circle the same throughout the whole pear? No, it's wider, it gets skinny and big, but everywhere, no matter where I slice, it's a circle. Do we know how to find area of a circle? Okay, so if we're trying to find these irregular solids, if we want their volume, we have to think about, if I sliced it, what shape am I looking at? And then we can use that to calculate our volume, because that shape is the same throughout, even though the size of it isn't. Okay, it may increase and decrease as you move along your x-axis. So we could think about, if I take my pear and slice it into a bunch of different chunks, we could find the volume of all those little chunks and add them together. And the more accurate we would be, what would have to happen to my slices? They would have to get smaller and smaller. And ultimately, to get as accurate as possible, my slices, the number of slices would have to head to infinity. And as the limit of the sum goes to infinity, this is turning into an integral. We are integrating the area of one of those slices. Right? So that is how we will calculate these volumes. So the volume is the sum of all these areas, which we know is an integral. And we would have to have some kind of starting and stopping point. So like from A to B, or here. I think I have it on the next slide, so let's just write integral. We have to integrate if we want to calculate this. So here is our volume. We could do all those different sums, or we could just integrate from A to B of the area of a cross section. Now, the area of the cross section, we can't just have a number because those cross sections change. So we'll have to find a formula to calculate that area and integrate that. So we're going to start out proving something we already know. Volume of a sphere. I've told you all year it's 4/3 pi r cubed. You guys have always wanted to know why, right? So we know a sphere. When I say sphere, what am I talking about? A ball. Now, I do not draw three-dimensional shapes very well, so I'm going to draw a circle to visualize this. I hope you guys are okay with that. So pretend this is a ball. if I'm trying to find the volume of this ball, we have to think about what a cross section would look like. All right, if you take a basketball and you slice it, and then you look, what shape are you looking at? A circle. So my cross section would be like if I cut this side off. We are looking at a circle. And we know area of a circle is pi r squared. Okay. In my sphere, if it's centered at 0, the distance to the edge, the distance from the center out is called the what? Radius. So no matter where we're at. So this would be r. This would be what if you're putting it on the xy axis? But we went backwards, so it would be a negative r. So we're going to integrate from negative r to positive r. And we have to integrate the area of a cross section. Okay, the r is where we're going to start and stop. So, if the cross section is a circle, how do we find the area of a circle? Okay. But we know the radius of this little circle is changing as we go, right? It starts off really small and it's going to get bigger as you get to the edge, and then it's going to start getting smaller again. So we need a formula for that radius. So we know it's pi times whatever my radius is squared. And we need to figure out that radius. We have the radius of the entire sphere is r. So if I were to think about a triangle here, the distance from the center to the edge of where my cross section starts is r, because that's the radius of the sphere. And however high up we are, if we're just thinking about xy, this height would be y, and this would be x. You go over x and up y. So if I'm trying to find this cross section, my green circle, the radius of that green circle is my y, right? Do you guys see that part? So if I wanted to solve for that, we know in a right triangle, a squared plus b squared equals c squared. The radius of my cross section is the height y, so if I solve for that, so y would be the square root, just a positive, if we're talking about the radius would be positive, of r squared minus x squared. All right, a little confusing because I'm talking about multiple radii here. I have the radius of the whole sphere and then the radius of that cross section. Are there any questions on what I've done so far? The hard part of these is the setup. What we've just done is the difficult part. Now we should be able to integrate. If we have a square root and a square, what happens? They cancel. I could pull my pi out in front, it's just coefficient. So we have pi times integral from negative r to r of r squared minus x squared dx. Okay, x is the variable. So when we integrate, r squared is just representing a number. So what's the antiderivative of r squared? R squared to x. R squared is just a coefficient, so it's just a number. Because dx tells me x is the variable, any other number is a constant. Minus antiderivative of x squared. If I put in an r, we get r cubed minus r cubed over 3. We put in a negative r, we get negative r cubed plus r cubed over 3. So that's 2r cubed minus 2/3 r cubed. 2 is like 6/3 minus 2/3, which is 4/3 times our pi r cubed. So that is the volume of a sphere formula that we've been using all year.
So why did we find out that we needed to solve for y on that one?
Because we were trying to find the area of this green circle. Okay, so if I were to flip my circle, the area of that circle is pi times whatever the radius of that circle is squared. So the height of that circle
Is the radius.
Yes.
Okay.
You're welcome. Other questions? Let's look at a problem. So I drew a beautiful picture for us already. We want the volume of the solid whose cross section at x is semicircular with a radius of x squared for 0 less than or equal to x less than or equal to 1. Okay, so this is my solid. And no matter where I slice it, okay, if you were to cut through, you're going to be looking at a semicircle. Okay, but that semicircle changes. As we go through our solid, it's getting smaller and smaller. So if I want to find the volume, we have to integrate. Where am I going to start and stop? And I'm integrating the area of that solid. Okay, how do we find if this is a semicircle? We know area of a circle is pi r squared. So how would you find the area of a semicircle? We have half of it. So pi over 2 r squared is the whole thing over 2. So we need to figure out an equation for the radius of that semicircle. So think about if we sliced it. I'm looking at this. How the radius is going to be the distance from the x-axis to the edge of our circle, right? And I'm looking at it here. It goes all the way up to here. What is the radius going to end at? It's on this line every time, right? That line is what dictates how big our circle is. What's the equation of that? I gave you part of the graph of x squared, and I told you that is the radius. With me so far? Then we can finish it from here. The pi over 2 is just coefficient. You can pull it out if you want. It'll be x to the 4th dx. What's the antiderivative of x to the 4th? So we have pi over 10 times 1 to the 5th minus 0 to the 5th. Pi over 10. 2 times 5. pi over 2 times 1 over 5.
I normally just ask this, but can I ask again where the pi over 10 came from?
Right here.
Oh! Okay, thank you.
Other questions? Let's try one more time. We have to create our own. This is where it gets fun. Find the volume of the solid obtained by rotating y equals 1 minus x squared, bounded by y equals 0, around the x-axis. Okay. This gets tricky at times. We have to figure out what this is even going to look like. It's very hard to calculate a volume if you don't know what your picture is. 1 minus x squared. What is that? Upside down parabola. Okay. Think of it as like a negative x squared, so that's upside down. Plus 1 would move our parabola up 1. So this is our picture. But if I said it's bounded by y equals 0, y equals 0 is the x-axis. So that's the only part of this graph I'm looking at. Now, we need to find where we're going to start and stop here. We have to start here and go to here. Okay, if we're traveling, if x is our variable, we're moving along the x-axis, so we need our left and our right points here. How would I find those points? I need to know when my function is equal to 0. So that's when x squared is equal to 1, so x is plus or minus 1. If you take this parabola and we are rotating it around the x-axis, so if I take that u and start spinning it around the x-axis, what are we forming? If we want, there are, because my illustrations are not always the best. I'm going to look at this site here, if it'll load. Okay, so my function was 1 minus x to the second. And we decided we were going from -1 to +1. Okay, so this is kind of what it looks like. It's showing an XYZ plane because the Z is representing our height here. As we start rotating this thing around the x-axis, it's spinning like this, so we can see it created an egg kind of shape. Okay, not a perfect sphere, but definitely round. If you take the cross section of that, so if I slice it right here, what am I looking at? A circle. Can you guys visualize that? Does this help? No? There's another one, but they're very similar. This one just has a different perspective on it. So here's 1 minus x to the second. So if I took this and I just start spinning it, I have some different things set on this one. This one you can like animate and it's showing you as it spins. Now it doesn't allow us to go to the negative, so it's only showing us half of it. But you can kind of see it in motion as it goes. All right. So we know we're getting a sphere. We know then our cross section is a circle. Cross section would be measured right here. When we integrate, we're going to go from where to where? -1 to 1, because we have to start on one end and we have to do our cross sections all the way till we get to the other. We said we're integrating the area of a circle, so that's pi times the radius squared. So the big thing is finding out the radius. We know the area of the circle is pi r squared. The radius of the circle. The x-axis is the center because that's what we're rotating around. So the radius goes from the center out to the curve. What is my curve? This is my 1 minus x squared. So the equation for the radius is the 1 minus x squared, because the radius is going to go from the x-axis up to that curve as you move along.
The last two examples, the function has been out. Is that Sarah?
When we are, for today, yes. Okay, if we're rotating around the x-axis, then yes, it's going to work out that way. All right, so the pi could come out. Let's just FOIL this out so we don't have any substitution or anything. So that would be 1 minus 2x squared plus x to the 4th dx. Okay, antiderivative of 1 would be x minus plus okay, if we plug in a 1, we get 1 minus 2/3 plus 1/5 minus, we put in -1, we get -1 plus 2/3 minus 1/5. And pi over 15. Maybe. I trust my math. Of the solid obtained by rotating about the x-axis, the region under the curve, y equals the square root of x from 0 to 1. All right, so my function is the square root of x. What's the square root graph look like? Okay. But we're not going forever. We're only going from 0 to 1. And then I'm stopping it. Okay, so we have this section. If you take that little piece and start rotating it around the x-axis, what's it going to look like? If we wanted to do this, it is super slow. Alright, so we are going, this was the square root of x. We're going from 0 to 1. So that's our graph, and then as we start rotating it, it's forming like a cup or a bowl shape. A cross section is what shape? circle. That's what we're working on today. All of these are circular as we rotate them. So we would get something like this. We know we're going to go from 0 to 1. Area of a circle is pi times our radius squared. The radius, if you take any cross section throughout here, it's a circle. The radius is going to be the distance from the x-axis up to the curve, and the equation of our curve is square root of x. So the function is giving us our radius. Alright, so if we do that one, the pi square root of x squared is x dx. Antiderivative of x is pi over 2, 1 squared minus 0 squared, pi over 2. Any questions so far? So I am stopping here today. I want you guys to do